Let us now work a second calorimetry problem. This one a little more difficult in terms of algebra because what we're going to look for this time is the temperature final. So let me read the question and walk you through that question in terms of the shown diagram. In this one, 3.16 grams of salicylic acid, C7H6O3, is burned in a bomb calorimetry. That bomb calorimetry contains 5 kilograms of water at 23 degrees C. We know that after burning the salicylic acid, the amount of heat released was 69.3 kilojoules. We also know that the heat capacity of our calorimeter is 3255 joules per degree C. The question is, what is our temperature final? Again, this is a simple calorimetry problem, and so we're going to start with that generic formula. Q lost equaled Q gained. This may be put in many terms. Q in equal Q out, Q absorbed equal Q emitted, in whatever form you would like to put it. But the essence of the idea, of course, is that something or some things are going to lose heat, and something or some things are going to gain heat. Find expressions for Q for everything that loses or emits heat, and set that equal to expressions for Q for everything that gains or absorbs heat. Now, because there's a lot of algebra, I've chosen to go ahead and set the problem up for you. Q lost is the heat of reaction for which we already know the value. The two items that gain heat are the calorimeter and the water. And so all we need to do at this point is find an expression for the calorimeter, find an expression for the water, add those two together, and set them equal to Q reaction. As you can see from here, we do some basic algebra and isolate delta T. I'm now at this point between this third and fourth equation merely going to substitute numbers and solve these equations. One note on significant figures, although this shows that it's good to one significant figure. If I put a dot here, would be equal to 4. So I'm just going to use whatever number is in my calculator. I'm going to punch out 5,000, but I'm going to remember the number was 5.00 kilograms, or 5,000 grams. So I'm just going to remember that that number is good to 3 sig figs and just leave the numbers in my calculator to ride, as it were. With that disclaimer, I'll substitute the mass in and put the specific heat for water. This portion in parentheses here simplifies to this number. To go from this 6th equation to the 7th one, I merely multiply both sides. I'm going to multiply both sides by degrees C divided by 24.2 kilojoules. Yes? So that's going to cancel this out on this side. And you multiply this times degrees C, and you get degrees C, and then you take 69.3 and divide it by 24.2, and you come up with 2.87 degrees C. That number is equal to delta T. I'm going to rewrite delta T now as T final minus T initial. I'm going to now merely substitute in for T initial, which means that expression is equal to T final minus 23. And just to keep it clean, I'm going to pull this this 2.87, and I'm going to rewrite it here at the end. So that the equation that I'm going to work with at the end of the day is this equation here. So this simplifies to T final is equal to 2.87 plus, because this is going to be moved over to the other side of the equation by adding 23 to both sides. So it's 2.87 plus 23 gives us 25.87 degrees C.